Alright, welcome back students. This is our last video about molecular orbitals, and in this video we'll be focusing on molecular term symbols. So molecular term symbols are going to be a lot like atomic term symbols. Much like atomic term symbols, molecular term symbols are going to represent different electronic energy levels or electronic states, whichever, those are synonyms, right? Whichever you want to use. Different electronic energy levels that arise from how we put electrons into orbitals, right? So the different ways we can combine both orbital angular momentum and spin angular momentum. Because remember that electrons are going to be affected by all the other electrons present. So how we put things into orbitals matters, both with regard to orbital angular momentum, right, little m sub l, as well as spin or m sub s. So we're going to use oxygen as our example. Here I'm not going to draw out the individual atomic energy diagrams. I'm simply going to go straight to the molecular orbital diagram. So this is the molecular orbital diagram, or the molecular orbital energy levels for oxygen. You'll notice that at a very low energy, we have two non-bonding orbitals that are degenerate. They're both 1s. And so this is, again, those 1s atomic orbitals, and they will be degenerate or very, very nearly degenerate. And then once we get into the valence shell, or the 2, n equals 2 shell of oxygen, we'll see that the 2s atomic orbitals from the two oxygen atoms come together to form a sigma Gerada and a sigma Ungerada star. And then as we continue to go up in energy, the two p orbitals on each atomic oxygen will come together. The two pz's will come together to form sigma Gerada and sigma Ungerada star at a higher energy, and the 2px and 2py will come together to form pi Ungeradas and pi Gerada star orbitals. So this should be our molecular orbital diagram. If we start putting in electrons, we should get that there are two electrons that are unpaired, or maybe unpaired. There are two electrons in the degenerate pi Gerada star, and so we get an overall bond order of 2, which is what we expect for oxygen. And so here we want to know, what are the molecular term symbols affiliated with oxygen? Much like with atomic term symbols, only the open shells matter, or the highest closed shell. So we're going to see that all closed shells will have the same the same term symbol, molecular in this case. Just like with atomic term symbols, closed shells have the same term symbol. Here, molecular term symbols, for closed shell, will also all be the same. But when we have these open shells, that's when we really get a variety of term symbols, and we have to think about using Hund's rules again to find that ground state. So here we're going to be thinking about two electrons in the degenerate pi Gerada star orbitals. And we want to know, what are the term symbols? The first step to thinking about figuring out the configurations and the term symbols is to think about which m sub l, and these are atomic little m sub l values, contribute to the pi Ungerada and pi Gerada star orbitals. So pause the video for a minute, see if you can answer this question. So 2px is one of the contributors to pi Ungerada and pi Gerada, and that has an m sub l value of -1. 2py is the other atomic orbital that's going to contribute to these pi states, and it has an m sub l value of +1. Remember that the 2pz, which has an m sub l of 0, contributes to forming sigma bonding and antibonding molecular orbitals. It doesn't contribute to the pi. So we're only going to have two possible little m sub l values, -1 and +1. There's no 0 here, which is a little bit different. So now that we know what our two different m sub l values are, we know that we have two electrons. They can each be either spin up or spin down without breaking the Pauli exclusion principle, so you can't put two spin ups together or two spin downs together in a single orbital. What are the possible configurations of having two electrons distributed across these two orbitals? So I want you to take a minute, think of all the ways you could possibly do that without breaking Pauli exclusion. So we should get that we can get three different values for our capital M sub s. Remember, this capital M sub s is the summation of all the possible little m sub s contributions, so from each individual electron. In this case, we have 2 electrons. If they're both spin up, 1/2 plus 1/2 gives us positive 1 for our capital M sub s. If they're both spin down, negative 1/2 minus 1/2 is going to give us negative 1 for our capital M sub s. And if one is spin up and the other is spin down, we'll have 1/2 minus 1/2, or capital M sub s equals 0. When we think about our capital M sub L, again, because we don't have a little m sub L of 0 contributing here, we could put 2 electrons in positive 1 and get positive 2 for our m sub L. We could put both electrons in the m sub L equals -1 orbital and get capital M sub L of -2. Or we could spread them out and put 1 in each. And 1 minus 1 gives us an m sub L of 0. So notice that we're missing some capital M sub L values here. We're missing positive 1 and -1 because of that lack of 0. Okay, so this is going to be a little bit different than atomic. So the first one that I thought of was putting them either both in the positive 1 or both in the -1. And in order to avoid breaking Pauli exclusion, one would have to be spin up and the other would have to be spin down. And so we could think about 1 plus 1 minus would be 2 electrons with opposite spins in the m sub L plus 1 orbital, or -1 plus -1 minus would be 1 up, 1 spin down, both in the -1 orbital. But then we could also put them into different orbitals and give them the same spin. So one could be in -1, one could be in +1, both being a spin up or both being a spin down, which are the two I've just added to the table. Or we could mix and match their spins. So we could have 1 in m sub L -1 and 1 electron in m sub L equals +1, with one being spin up and one being spin down, but we could also flip which one is up and which one is down. So we'll get 2 possibilities there. So we get a total of 6 different microstates. All right, so now that we know our microstates, how do we figure out our term symbols? So what was the first thing we did when we were figuring out atomic term symbols? We figured out what the highest value, the extreme value of capital M sub L would be. And so here, our maximum value of capital M sub L is +2, right? And whether or not we took the negative extreme or the positive extreme, the absolute value of that is 2. And our m sub s that's available, if we have m sub L equals +2 or -2, we only have one capital M sub s availability that pairs with that, and that's m sub s equals 0, which corresponds to s equals 0, or our spin, total spin. And here, sorry, this chart is kind of written over, but we have our chart here. What's going to go in the middle of our term symbol in the place of a capital letter, we're going to use Greek letters to signify that this is molecular and not atomic. And instead of putting the value of L, because you'll notice that we're missing values of m sub L, we're actually going to go with the absolute value of m sub L in the center. So that's another important difference, is what the letter that goes in the center represents the absolute value of m sub L as opposed to the value of capital L. All right, so we have absolute value of capital M sub L equals 2, which corresponds to a delta. So we're going to use a capital delta in the middle of our term symbol. Our multiplicity is still 2s plus 1. S here is 0, so we have 2 times 0 plus 1, or just 1. So we're going to get a singlet delta. So we'll put that superscript to the left of the delta. Our symmetry, so before with atomic term symbols, what was subscripted to the right was a J value, or this Russell-Saunders coupling. It's a little bit different when we go to molecular orbitals. Here, we're going to put a symmetry designation subscripted to the right. So the symmetry, we're going to take into consideration each orbital that we're using. So in the case of +2, we're only using one orbital, or of -2, because we've put both electrons with opposite spin, but in the same orbital. And each of these pi orbitals is a Garada. So we only have one orbital that we're using, it's Garada, so the symmetry designation here is Garada. So we'll put a subscripted Garada. Your book is going to talk about some superscripted plus and minus designations. We're going to ignore those. That is additional information that can go in your term symbol. we're not going to deal with this in the context of this class. So you can ignore the pluses and minuses in your book. All right, so we've accounted for the two states that I've marked with pink, right? So they have this singlet, delta, Garada term symbol. So our next highest value of M sub L, our next value that we have of capital M sub L is actually 0. And that's going to represent a sigma state. Sorry, that's the one letter you can't really see in the table. And so our highest spin value there we can think about is positive 1. So we could have an S equals 1, which will account for M sub S equals plus 1, M sub S equals 0, and M sub S equals minus 1. So this is actually going to cover 3 different microstates, all with the same capital M sub L value. And so our multiplicity is going to be 2 times S, or 2 times 1 plus 1, or a triplet. So we have a triplet sigma. And here the symmetry is Garada times Garada. So an even function times an even function gives us back an even function. So this remains Garada. So this is triplet sigma Garada. And this will represent 3 microstates, which we'll mark with yellow. Because we want to make sure that we're not double counting. So this can only count for 1. So you'll notice that we're left with 1 microstate left, and it has an M sub L of 0 and an M sub S of 0. M sub L of 0 and S of 0 is going to lead to a singlet, because the S, 2 times 0 plus 1, and sigma in the middle, because sigma represents M sub L of 0. And we're going to get a Garada, because again we have an even function times an even function. So an even function times an even function remains even, we get a Garada state. So our 3 term symbols that we get for oxygen in its ground electronic state are singlet delta Garada, triplet sigma Garada, and singlet sigma Garada. So in the next video, we'll look at using Hund's rules to figure out what is the ground state of oxygen.